This is a LLC converter, and I will show you how to simplify it. So we want to simplify the LLC converter because it's not linear. And in order to do a AC analysis, we need a linear circuit. So we will end up with a circuit that looks like this. So in order to get this circuit, you can see that we simply crosses out the MOSFETs and also the transformer and the rectifier. So I will first show you how to find the equivalent resistance here based on the resistance on the load. So we just removed everything at the left of the circuit. So we just have the transformer and the rectifier left. So we want to simplify it so we get this. Now I call this VP because it's the primary side. So on the secondary side we will have VS, right? And it's here. So this is actually a rectifier. It's just written in another way. So we just have two primary side windings instead of 4 diodes. So we can just replace this with a normal rectifier. So this is the same. It's just maybe a little bit easier to understand. So in order to find the RE based on RL, we can use the power balance here and here because they need to be equal to each other. So we know that IP squared multiplied by RE, because that is the resistance seen from this point. And this is equal to the output current squared multiplied by RL. So we can rewrite this equation and solve for RE. So we get that IO squared over IP squared multiplied by RL. So just move this equation up here. So we know that IO and RL are known. So we just need to find IP in order to solve for RE. I'm going to calculate IP in 2 steps just to make it simple. So we can first calculate the IP based on the current on the secondary side of the transformer. So the current here is IS. So the formula for a transformer could be written as IP over IS is equal to N2 over N1. And this could be rewritten as 1 over N. So if we solve for IP, and we get that IP is equal to IS divided by N. So now we just need to find the IS. So in order to find the IS, we need to look at the rectifier here because the current is being rectified. So if you search up the equation for the voltage over a rectifier, you will find VO is equal to 2 over pi multiplied by Vs peak, because Vs is the voltage over here. This could be rewritten as 2 over pi multiplied by the square root of 2 and then multiplied by Vs, which is the RMS value of Vs. But we want to find the ratio between the currents on the output and the secondary side. Because the load is resistive, we just assume that the capacitor is so high that we can neglect it. We know that the current IO should be equal to about the same. We just replace Vs with Is. IO is equal to 2 over pi and then multiplied by square root of 2 and multiplied by Is, which is the RMS value. So if we rewrite this equation, we can solve for Is, and we'll get that it's equal to IO and then pi over 2 square root of 2. Now we can just put this one into this equation and solve for IP. So we have IP is equal to, so we have Is, which is IO, and then pi over 2 square root of 2. And then we'll just divide by N. Now we can put this equation into the equation for RE. So we get that RE is equal to IO squared and then over this equation. So we also get IO squared. Yeah, and we need to square this as well. So IE squared. So we get IO squared over IO squared, which is equal to 1. So we just cross that out. And then we have 2 squared multiplied by this squared, which is equal to 8. So we can just write that. We have 8 and then over pi squared. and then multiply by n squared. And we also need to remember the RL. So this would be the equation for RE. So we can just rearrange this equation in order to get this. So now we've simplified the right side of the circuit. So we got the RE, and this is the equation. Now we're going to simplify the MOSFET here on the left side. So we just get a AC voltage. So I just removed everything on the right side that we don't need. So here we have two MOSFETs. So it could be either on or off. So the voltage, VIE, would be equal to a square wave form, where the maximum is equal to VI and the minimum is equal to 0. So if we found the Fourier series for the voltage, we will have 2A over n pi multiplied by sine of n pi over 2. So this is the general equation for the square waves. And the amplitude here, A, is equal to the peak-to-peak value, which is VI. And we only want to look at the first harmonics for this scenario. So we have 2 and then multiplied by VI, and then we divide by pi, because we want to look at the first harmonic, so n is equal to 1. When n is equal to 1, we have sine of p halves, which is equal to 1 as well. So we can just multiply this with 2, no, with 1. So this is the equation for the voltage source. The reason why we only look at the first harmonic is because we're simplifying the circuit, so we can do a AC sweep. The reason why we look at only one harmonic is so we can translate this to a one AC source. And by only looking at one harmonic, it is easier to look at the circuit and find the different parameters that we need. So now we've simplified the LLC converter, and we got this circuit here with only one AC source, where the value, RMS value, is this. And we also get a resistance on the load side, where the value is this.